Hello everybody and welcome to yet another Calculus 1 video. In this video I will be going over two sections worth of calculus in one video. We will be covering section 3.3 and 3.4 in the same video, as there are a lot of similarities between these two sections. In 3.3 we will be talking about intervals of increasing and decreasing where a function is increasing or decreasing. And then we will use those intervals in the first derivative test to find out where relative extrema are. And in 3.4 we will be finding intervals for which a function is either concave up or concave down. And we will use those intervals to figure out where inflection points are, and this will all be defined for you soon. And we will also use these intervals to figure out how to use the second derivative test, also used to find extrema. Let's jump in. So first I'm just going to go over the process here. How do you find intervals where a function is increasing or decreasing? Well, the first thing you need to do is find the domain of the function. So that way we know what intervals are actually possible. Some functions don't have all real numbers as their domain. So knowing the domain that we're working with will be very helpful. The second part, or the second step, finding critical values. And so you can see from a couple sections ago, critical values playing a big role right now in this unit of calculus. Step 3, we will create a sign chart, and then we will test values in the derivative to label each interval as either increasing or decreasing. And the way we do that is by noting if the derivative is greater than 0, which means positive, then the original function is the function that's doing the increasing. If the derivative is negative on that particular interval, then the function is decreasing on that interval, and if the derivative equals 0 for that entire interval, then the derivative is constant. And to be honest, this one normally doesn't show up. Maybe in some crazy piecewise function example, constant normally doesn't show up. All right. Let's look at some examples. To start off the examples, we have this example here that asks us just to find the intervals on which the function is increasing or decreasing. So here's our function. That's good to know. We have it right. I wonder if I can do this. There we go. We have it right here. And the first thing I want to do is find the domain for this function. And again, the purpose for finding the domain I'll get to in a second here. I can see that we have a variable in the denominator. That means x cannot equal 0, which means the domain looks something like this. And the importance of finding the domain is so that when we find critical values and we get a number that's not supposed to be in the domain, then we can make sure a little later on that we can exclude it from being a maximum or a minimum. Like if we get 0 being a critical value, since 0 wasn't part of the domain, well, we know there cannot be a maximum or a minimum at x equals 0. And we'll get into that a little bit later, but for now, just intervals of increasing, decreasing, and constant. So the next thing we have to do is find the derivative. So we found the domain. I think the second step said find the critical values. Well, you have to find the derivative to find the critical values. So we have to find the derivative, which means we should rewrite the function like this. F of x equals x plus 9 times x to the negative 1 power. Now again, the negative 1 is only the exponent for the x and not the 9. So when you find the derivative of this, f prime of x will equal 1 minus 9x to the negative 2 power. And then we have to shove that negative 2 power exponent x and all of it to the bottom. So we have 1 minus 9 over x squared. And again, when you have a derivative, after you find the derivative, the first thing you want to do is look at where the derivative is undefined. So I can see, just like the original function, and I'm going to point it out again, since the original function had a discontinuity at x equals 0, the derivative has a discontinuity at x equals 0. It's pretty cool how that works. All right, so we already know then that we have a critical value at x equals 0. And that is because that is where f prime of x is undefined. Now, the second piece to this is, where does this derivative equal 0? So we will take this derivative, set it equal to 0, and solve for x. So I will multiply by x squared, everything by x squared. So I'll get x squared minus 9 equals 0. And work. I think you guys can see from here that x will be plus or minus 3. So here are the other two critical values. So we do have 3 critical values here. Now, based on how we defined whether a function was increasing or decreasing, we have to use the derivative to figure it out. So what we do is we create a sign chart. So let me bust out my ruler again here. So there we go. I have a number line. And what I'm going to do is I'm going to put my critical values right here. So I've got -3, I've got 0, and I've got 3. This is clearly to scale. Just make sure your numbers are in the correct order, left to right. Negative numbers on the left, positive numbers on the right, so on, so on. So from here, we have to put the critical values on the number line, and you can see that these critical values divide the number line into 4 different intervals. So over here I have interval number 1, over here I have interval number 2, and that's between -3 and 0. Over here I have interval number 3 between 0 and 3, and over here I have interval number 4 from 3 to infinity. Now it is our goal to figure out whether a function is increasing or decreasing on this interval. And we do that by picking any value in that interval. So over here to the left of -3, I think I'm going to pick something like, I'm going to pick -5. And you get free reign. You can pick -6, you can pick -4, you can pick -1,000,000. It doesn't matter, just as long as it's to the left of -3. In between 3 and 0, -3 and 0, I'm going to pick, let's say I pick -1. In between 0 and 3, I'm going to pick 1. And let's see, just pick a number to the right of 3, I'm going to pick 4. So now, since we have to use the derivative to describe the original function, we are using the derivative to tell whether the original function is increasing or decreasing. I have to figure out what is f prime of -5. And honestly, the number doesn't matter as much as the sign does. So I just need to know whether it's positive or negative. If you go back and look at step 4, it says if f prime is bigger than 0, then the original function is increasing. So when you substitute negative 5 into the derivative here, you will get 1 minus 9 over a positive 25, which ends up being positive. So I know here this function is increasing in this particular interval. The next interval between negative 3 and 0, I picked a negative 1. If I put negative 1 in here into the derivative, f prime of negative 1, I will get, what is that? Negative 1 squared is 1. 9 divided by 1 is 9. So I'd have 1 minus 9. Boy, that's a negative 8. This would be negative. So this would be decreasing. And you do this for all of the intervals, all at the derivative. So let's see, 1, that would be the exact same thing, negative. And then over here, when you pick 4, f prime of 4, that would be positive. So we know that it is decreasing here and increasing here. So how do we write this answer out? You will simply, over here with the answer, write out the word increasing and decreasing and just list the intervals where the function is increasing and decreasing. And I really, really, really need to point out, like I am going to, I don't know, highlight or say it 15 times, I don't know. The only numbers that will be in your increasing and decreasing intervals will be critical values. Critical values will be the only numbers that appear in your increasing and decreasing intervals. Also, you will find the open intervals for which a function is increasing or decreasing. So you will always be using parentheses. And you can see again here that these are the only numbers that show up. They are the critical values. Let's take a look at another example. Our first example. Find the intervals on which the function is increasing or decreasing, and you may see an extra word here sometimes when we say find the open intervals on which the function is increasing or decreasing, and that's fine. But first I want to talk about the domain of this function. As mentioned in a previous video, whenever you have a square root of a number squared, or a perfect square number, minus x squared, this represents a semicircle. And since it's positive, it'll be the top half of a semicircle, or the top half of a circle, the top semicircle. So let me just make that note right here. All right, there you go. So the first thing we want to do is find the domain of this. So we know the domain is going to be restricted by this square root factor. And since we know that this represents the top half of a circle with radius 4 centered at 0, 0, we can see a picture in our head that the domain here would start at negative 4 and go all the way over to positive 4. If you go 4 left and 4 right from the origin, you'll get negative 4 to 4. The next step here is to find the derivative of this function. And there's a lot going on here. So the derivative will require us to use the product rule, but then we can also rewrite this as this, where we take the square root and turn it into a 1/2 power. So you can see here that this is going to require using a chain rule. So here I have my first function because I have a product rule. This is my f of x. Here I have a second function. This is my g of x for my product rule. So I'm just going to find f prime of x and g prime of x off to the side. Well, f prime of x, pretty simple. That's 1. G prime of x is going to require the chain rule. And that will be 1 over 2 times 16 minus x squared to the 1/2 times negative 2x. And again, this derivative should feel similar to another derivative I did in a previous video. We can simplify this by dividing these 2's, and then we can also push this x and the negative into the top of this fraction. So it'll end up being negative x over this entire denominator. So the derivative will look like this. There's your derivative. That is the calculus. That is all the calculus that is done in this entire exercise. All right. So that being said, we now have to find the critical values. And I know on the previous slide, finding the derivative was not a step that was listed, but it is necessary to do in order to find the critical values. So right now, we are only looking for critical values, again, that are between these two numbers. And so what we should do, of course, first thing, since we have the derivative in front of us, is look for where the derivative is undefined. Well, I only have a denominator here, or here, so I can set that denominator equal to 0 and find out where the function is undefined. Rather, the derivative is undefined. So that means what? 16 minus x squared equals 0. I can write, if I wanted to, the parentheses here with the 1/2 power, but I would just square both sides to get rid of it, and 0 squared is 0. So I'm just going to leave it here. The next part would be I could add x squared to both sides and take the square root. And there are two critical values, but those critical values are not between -4 and 4. They are -4 and 4. So we don't need these. So the only other thing that we have to do now is college algebra. And that is, or pre-calculus, and that is solving this equation when we set it equal to 0. Let the algebra commence. I will release steps about every 5 seconds with some explanation as to how to solve this equation, just for the brevity of this video. But you're more than welcome to pause it and try solving it yourself. And so with this final step, you can see that -16 equals 0 is what we get after we do all this math. We get -16 equals 0. Let me quickly walk through these steps. So I combined these by multiplication, x times -x. That's how I got the -x squared here. And I multiplied all the terms by 16 minus x squared to the 1/2 power to eliminate the fraction. So when I did that here, that got rid of this. When I did that here, it became 16 minus x squared to the 1/2 power times itself. That's why the square was here. equals 0 times anything is just 0 on this side. And from here, I think all of steps are pretty self-explanatory. But what this means then is that this tells us there are no critical values for this function. In the open interval -4 to 4. So how do we go about finishing this exercise? Let's take a look at how to finish this on the next slide. But before I do, I have to go back and make a very quick correction because I picked it up as I was editing the next slide. There is a big fat correction right here in the derivative. That being, I did the product rule incorrectly and put a minus here. This should be a plus. That doesn't change too much throughout the derivative or the solving process. All of these minuses become plus, and then this minus also becomes plus. So if you made it this far into this slide without firing me an email or a text or asking people in GroupMe, congratulations. Let's take a look on the next slide how to do the rest of this exercise. The correct way to go about solving this kind of oddball example here is to make sure you still put your critical values on a number line in the correct order. -4 is on the left of +4, so here we go. Go back and take a look at the domain again. The domain says that the function and its derivative, to be honest, only exist between -4 and +4. So it would be silly for us to pick a number left of -4. The function does not exist out there. It would be silly for us to pick a number that would be greater than +4 because the function does not exist there. So the only interval we have to worry about is what's in between 4 and -4. So this makes it pretty simple. We can just pick 0, which leads me to this little hint. If you can, pick 0. Then 1, then -1. Again, if you can. Those are 3 of the easiest numbers to work with. You're always more than welcome to pick 3 or -3, but 0, 1, or -1 are going to be the easiest ones to work with. Now, if we find f prime of 0 from the function on the last page, which is brought over here for your convenience, with the correct sign, I promise. When you substitute 0 into this derivative, you'll notice that the first term just becomes 0 because you have a 0 in the top of a fraction, but it just becomes 0. The denominator is not 0, so we're good to go there. But when you substitute 0 into this x, you'll get 16 minus 0 is 16. The square root of 16 is 4, and it'll be a +4. So the derivative f prime of 0 is +4. Ooh, let me take a second just to remind you what this statement means here very quickly. The slope of the tangent line at x equals 0 for the original function is +4. The slope of the tangent line is +4 when x equals 0. But the point here is that it is positive, so this function is increasing all the way from 4 to -4. So our answer would be increasing open interval -4 to 4 and decreasing no intervals. So there you have it. Let's continue with the lesson. So, new material, big air quotes, new material. On this slide, you can see that one of the slides, this looks identical to one of the slides that you've already seen. And this little bit has been added. And this little bit down here is what I would say is the first derivative test. So you need to do all of these things first. Find out where a function is increasing or decreasing, and then we can use the first derivative test, which says as long as f is defined where a function changes y patterns, and I'll explain that in a second, then f has a max or a min. So when I say when the function changes y patterns, I mean where a function changes from increasing to decreasing, right? The y's changed, or where a function changes from decreasing to increasing. Now, this being a calculus class, we now can notate whether a function is increasing or decreasing using this notation, using the derivative. So using derivative notation, we have if f of x changes from positive to negative at x equals c, then f has a relative maximum at x equals c. And I think that makes sense. If a function actually changes from increasing to decreasing, there's a maximum. Similarly, in the blue ink, so we can follow along here, if f prime of x changes from negative to positive at x equals c, then f has a relative minimum at that point c, f of c. So if you go from decreasing to increasing at that point, then there's a minimum. And this condition I put here, as long as f is defined where a function changes y patterns. So there has to be a point there. This little phrase here negates any chance that a vertical asymptote will make this list. Because you very well could have a vertical asymptote and have a function that increases and decreases. But there is no maximum here in the middle. There is no minimum here in the middle because it's a vertical asymptote. There is not an actual point there. So I have to make that little stipulation as long as f is defined. Let's look at some examples. All right, for this particular example, we are trying to use the first derivative test to find relative extrema for the following function. You can see it here. This is a polynomial, so the domain is all real numbers. Here's the first derivative already, and to find the critical values, you set the derivative equal to 0. So I preloaded this slide with all of this work. Just so that I could stop here and show you how to solve for x, I'm going to common factor a 3x out of both terms, and then I will be left with an x minus 4 equal to 0. So this tells me that x will equal 0 and x will equal 4. Now, that being the case, we now set up our number line, and I'm going to pick 3 values. I will pick -1, I will pick +1, and I will pick, let's say 10. Why not? So what I will do then is I will come over here to the derivative that I have found, and I will substitute these numbers in here and see what I get. Increasing, or positive, negative, let's see what happens here. So I will have f prime of -1 And if I do all of that work, it'll end up being 15. But the fact that we're interested in is that that 15 is positive, so this will be increasing. If I pick 1 and find f prime of 1, I will get negative 9, which is negative, and that's what we're interested in. So this interval will be decreasing. And then if I pick 10, I don't know what that number is, but it's going to be pretty easy to see that f prime of 10 is positive, aka it can be written like this: f prime of 10 is bigger than 0, which means this interval is increasing. Now, that's the intervals of increasing, decreasing, constant. There they are. But since this question is not asking for what are the intervals where this function is increasing or decreasing, it is asking for us, to find the relative extrema for the following function. What that means is we have to take a look. We have to take a look at our 0 here. Does it change? Do the y behaviors change? Well, to the left, it's increasing. To the right, it's decreasing. Yep, that's a change. So what that means is, and you can almost see it, increasing to decreasing means there should be a maximum. So we can say then there's a relative maximum of, we'll get to that, at x equals 0. We'll get to this blank here in a second. But just like we found a maximum here, does the function change y behaviors at x equals 4? You know what it sure does. It goes from decreasing to increasing. That's a change, and it happens at x equals 4. So we can also write there would be a relative minimum of something at x equals 4. So what goes in these blanks? That's a really good question. So how do you figure out what goes in these blanks? Well, a relative minimum and a relative maximum, these describe f of x, the original function, way back up here. This is describing the original function, all right? So it would make sense, if we're trying to find a maximum or a minimum of a function, we can take the values we got and substitute them into the original function. So if I substitute 0 into this function, I get 15, and 15 is the maximum, the relative maximum value. If I take 4 and substitute it into this function up here, the original function, because we're trying to find a max and min of the original function, if I substitute 4 in here for the original function, you'll get, I think it should be negative 17. I just did a bunch of mental math, and hopefully that is correct. But these also represent points on the actual function itself. So I did not say it, and I'm going to say it now. 0 is in the domain of this function. 4 is in the domain of this function. So we can say that there are maxes and mins at 0 and 4. Another thing is that these this last little bit here, when I switch to red, there we go. This last little bit here, the relative maximum of 15, that describes a y value. We have an x value. We can represent this as 0, 15. That is on the original function. So we could say relative maximum at 0, 15. We could also say relative minimum at 4, negative 17. All right, let's take a look at another example. All right, here we have another example We want to use the first derivative test to find relative extrema for this new function that is x minus 3 to the 1/3 power. So the domain is all real numbers. There are no square roots, no even roots. This is a cube root. And there are no variables in the denominator. And it's not a piecewise function, so we're good to go. The domain is all real numbers. And even on top of it, just for fun, this function is continuous. All right, so with that being said, I've already found the derivative again by the chain rule. The exponent comes to the front. There's the 1/3 that used to be here. If you subtract 1 from this exponent, it's negative 2/3, so this entire thing would get booted down to the denominator. Now, right off the bat, when you find derivatives and you're trying to find critical values, you want to find if a function is undefined anywhere first. And I can see right now that we would want to be setting this equal to 0, 2/3 equal to 0. Divide by 3, so x minus 3 to the 2/3 power equals 0. Raise both sides to the 3/2 power. Guess what? That just gets rid of this one. X minus 3 equals 0 and x equals 3. So there's one critical value. It is x equals 3. And as a matter of fact, that will be the only critical value. Let me bring back a little knowledge that should have been dropped on you in a previous course. If you take the derivative 1/3, or we'll say a rational expression, 2/3 equals 0. And you can go back and look at any example I've done so far. You can quite literally just set the top equal to 0. Because my first step anyway is going to be multiply by 3 times the quantity x minus 3 to the 2/3 power. And that's going to get rid of this, and it'll just stay 0 over here. So 1 equals 0. If we set the derivative equal to 0, that produces no new critical values. So there's that. So we bust out a number line and we continue our way with the increasing and decreasing intervals. So I have my number line. I put here my critical value, 3. I see that breaks my interval or my number line into 2 intervals, less than 3 or greater than 3. So I pick 0 because 0 is always going to work out nicely. Substitute 0 in here. Get some wonky looking fraction, but I know it's going to be positive because a 2 here means we are squaring, and squaring always turns any number, negative number, or any number into a positive number. To the right of 3, greater than 3, I picked 7. And if I put 7 in here, 7 minus 3 is positive. Squaring makes it positive. Cube rooting keeps it positive times a positive 3. It's all positive. So in this example, I have a critical value of 3. And at the critical value, to the left, it's increasing. And when I get to the critical value, it keeps increasing. There's no change from the left to the right. It's increasing, and then at 3 it just kind of stops and hangs out for a second. After that it keeps increasing. So since we don't have any change here, what that means is that we don't have, we have no relative extrema. And you should be able to look at a graph of this original function and see that there is no relative extrema. It is a cube root function that was shifted to the right 3 units, and it does something like this. It is always increasing, therefore there are no relative extrema. No maxes, no mins. Now we have worked our way into section 3.4, which is the intervals of concavity and the second derivative test. So just to get this out of the way up front, for the intervals of concavity, do everything you were just doing for the intervals of increasing and decreasing. All the same steps, except you do it with the second derivative instead of the first derivative. So when you find the critical values, you're finding the critical values of the second derivative. And then you go on and find your intervals. Just do everything exactly the same, but it's with the second derivative. When you find points of inflection, which I will define here for you in a moment, you will it will be very similar to finding the max and the min using the first derivative test, but you guessed it, you use the second derivative instead. So like the process here is already in you from the rest of this video. The only thing I need to do that is extra is define what concavity means in a very non-mathematical way to get you the idea of what it looks like. I want to show you how concavity changes what a graph looks like, whether it is increasing or decreasing. And then I want to define what an inflection point is, and then we can get right into examples. So let's look at those last little bits of information you need before the examples. All right, so here on this slide you can see we have a few things here. In the top portion I have inflection point, and I will define that for you in a minute. I will informally define what concavity is doing, and then we can go over what this means down here in a few seconds. So an inflection point is defined as a point C comma f of c, so that either f double prime of c equals 0 or f double prime of c is undefined. Remember, we're in that 3.4 idea now, second derivatives. The thing that needs to be made absolutely 100% clear is that an inflection point is in fact still a point. It must exist on f of x. It must exist. So if we work through and we find a value that makes the second derivative 0, but that value is not in the domain of the original function, then we cannot call it an inflection point. If we find a value that makes the second derivative undefined, and it is not in the domain of the original function, then we cannot say there is an inflection point. So that domain idea is very much in play here. So informally, what concavity looks like is it's kind of analogous to the way you learn that parabolas either open up or down. So if a parabola is opening up, what really we mean is a parabola opening up is what we would say concave up. And a parabola that's opening down, something like this here, this would be concave down. It's basically telling us which way is the function opening. Now when you look at this next graph here, this graph is opening down to the left and down to the right, but here in the middle it looks like it's opening up. And I'm going to see if I can do something here real quick. Alright, I have my handy two little sliders here that can help me out. Let me see if there we go. Alright, so I would say as we travel from left to right on this graph looks like between here being infinity and right about there maybe. It looks like just this piece of the graph is opening downward. So what I'm going to do is I'm going to mark that with a we go with a red dot right there. When I move these sliders over a little bit, it looks like between that red dot and, ooh, this is not working as well as I wanted to. Maybe like right there. Yeah, that looks good. All right, so between that red dot and this red dot right about there, it looks like the function is opening upward. And then if we travel just a little bit further to the right, it looks like between that red dot and positive infinity, the graph is opening downward. And that is the goal of concavity, is we are trying to figure out basically, is the function opening up or down, and where does it change? So this and this would be inflection points because the concavity changes. So here it's concave down. Here it's concave down. But here it is concave up. So if we can actually find a point on the graph where the concavity changes, we can call it an inflection point. Now, if you look at the last example over here, this portion of the graph is in fact concave down. It is opening downward. One of our arrows is going down, the other one is flattening out at a horizontal asymptote. That's fine. It's still concave down. So what's happening here? Let me write that. However, the left side of this graph is concave up. It is opening upward. Now, you can see the difference here. The concavity changes at this vertical asymptote, but we cannot say it changes at a specific XY coordinate pair. So even though the concavity changed from downward to upward at this particular X value, let's call it C, why not? We cannot say that this graph or this function that represents this graph has an inflection point. Cool. All right. So now lastly, there are ways to have concavity for when a function is increasing or decreasing. The concavity can look different. So for increasing, you see here, a concavity can either be up, and you can see that it is opening upward. We have an arrow going upward, and down. Eventually this would curl right back down. That's what it looks like the pattern is doing if you kind of continue it over here. That's what it looks like it's doing anyway. So it's opening downward. So it's still going up left or right, but it is opening downward. And then we have the same thing for when it's decreasing. It's going down left or right, but opening upward. And decreasing concave down, it's going down left to right, and it is concave down. So I hope that clears it up. Let's get into some examples on how to find where a function is concave up, concave down, and find some inflection points. All right, first example. We are going to find the intervals of concavity and any inflection points. So the first thing I want to do is remember that when you're finding inflection points or intervals of concavity, is that you want to very much treat this like a first derivative test. So I want to find that domain of negative infinity to infinity. There are no square roots, no jump discontinuities, because it's not a piecewise function, and there are no x's in the denominator. So negative infinity to infinity, here we go. The one little caveat I'm going to make about this is that I don't want to do the chain rule and the product rule here. You can see there'd be a product rule and then a chain rule within that. I'm not about that life right now, so I'm just going to do what I'm going to do. And I'm going to multiply out this x minus 2 cubed, and it'll be this here. That is plus 12x, that is minus 8, times x minus 1. Then I will multiply those two factors together to get x to the 4th. Let's see, minus 7x cubed plus 18x squared minus 20x and plus 8. So then I can say the first derivative, f prime of x, there we go, 4x cubed minus 21x squared plus 36x minus 20 by the power rule. I'm going to find the second derivative then, 12x minus 42x, there's a square here, plus 36. Then I can just go ahead and set that equal to 0 and start solving for x. I'm going to say divide all terms by 6, 2x squared minus 7x plus 6 equals 0. Then I can factor this. It is quadratic. It'll be 2x minus 3 and x minus 2. And then that tells me that I get two critical values. That'd be x equals 3/2 and x equals 2. So then what I can do without my ruler is mark these down. Let's say 3/2 and 2. So you can see this still looks and feels like a first derivative test, except, we're going to be using the second derivative. So I'm going to pick 1. I will pick, I guess 1.75, and I will pick, how about 3? That's fine. So we are evaluating the second derivative at all of these values. And if you substitute 1 into the second derivative here, you will notice that the second derivative when x equals 1 is positive, and I represent concave up like this. You can substitute 1.5 into the second derivative and figure out that it is negative, and I represent concave down like this. And if you substitute 3 into the second derivative, you'll get that it is positive, which means it is concave up on that interval. All right, so how do we answer everything here? So we can say concave up, and we have two intervals where this is concave up. It would be negative infinity to 3/2, and then from 2 to infinity. We can say this is concave down from 3/2 to 2. And again, just like with the first derivative test, we have the critical values are the only numbers that show up in your intervals. Lastly, the inflection points. Oops. We need an x and y coordinate, and to be clear, inflection points are points that are on the original function. So we know where they are happening. Inflection points happen where concavity changes. So here, this is the inflection, or rather the concavity changes at 3/2 from positive to negative, and the concavity changes at 2 from negative to positive. So what we have to do then is we have to substitute these x values that we already know into the original function to figure out that the y values are going to be 0 and negative 1 over 16, respectively. Let's take a look at that next example. For this example, same thing, find the intervals of concavity and any inflection points. So here is the function. Again, most of the time when you have a trig function, you will be given the domain, so there it is. So here's the first derivative of this, here's the second derivative of this, and now we just have to take this second derivative and set it equal to 0 and solve for x. How hard could it be? Haha, how hard can it be? Well, I think the first thing I want to do is divide by negative 1 to get sine of x plus cosine of x equals 0. Then I will subtract cosine x from both sides to get sine x equals negative cosine of x. Now, essentially what we're trying to do with this particular equation is find where the sine values and the cosine values are the same numbers but have opposite signs. So recalling back to the unit circle, if you have cosine comma sine for any point on the unit circle, we know that cosine and sine will have the same values here in the first quadrant. We know the cosine and sines will have the same values here in the third quadrant. So our only answers can be in the second and fourth quadrant. That being said, I want to at least get this down so it would be negative, positive. So you can see the sine and cosine would have this opposite signs here, and this would be positive, negative. All right, so we've got the opposite signs here, so it can't be there, it can't be there. But we need to make sure that they are exactly the same number. The only time that happens is when you have the 45-degree line like this. So this tells us then if we are trying to find this angle and we are trying to find this angle. So this would be 3 pi over 4 and 7 pi over 4. And they're both of these are on this interval. So these are our critical values. So we set up our number line. We don't want to go outside of the domain 0 to 2 pi. I'm going to pick 3 over 4, right? And they're not pick. I'm going to mark 3 over 4 as a critical value and 7 pi over 4 as a critical value. And you can see we have some intervals now to work with. So we just have to pick values between 0 and 3 pi over 4. Now you know that the over 2, the pi over 2, are good ones to use because those will be easy to figure out in a trig equation. Here I will pick pi, and this last one between 7 pi over 4 and 2 pi, if you remember the unit circle, there's only one angle that is in between these two. And that, there are infinitely many angles, but the one angle that everybody knows here would be 11 pi over 6. So why don't we use 11 pi over 6. So again, since we are working with the second derivative, we will be using the second derivative to find the concavity here. So I will say f double prime of pi over 2. F double prime of pi over 2. If you substitute pi over 2 in for x here, you'll get 1 for the sine of x, and it becomes negative from this. And if you substitute pi over 2 in here for cosine, you get 0. So that'll be entirely a negative interval, so concave down. If you pick pi and substitute pi into these x's here, this will be 0. Sine of x, sine of pi is 0. Cosine of pi is negative 1, but we negate it, so it'll become positive 1, which means f double prime of pi is positive, so concave up. And lastly, we have f double prime of 11 pi over 6. And when you do the math again, it becomes negative. So we can say the following things here. We have, I'm going to put my answer in this box here. We have to have concave up, and that only happens from 3 pi over 4 to 7 pi over 4. We have concave down from, let's see, 0 to 3 pi over 4, all the way to 7 pi over 4 to 2 pi. And then we have inflection points. And the inflection points are, again, are where the concavity changes. And inflection points are only on the original function. Again, inflection points happen here. So when we try to find inflection points, we are going to use, oh, maybe I need to point this out again. The only values that showed up in our intervals here are the critical values that we had way back here. So the inflection points are going to have the x values that are critical values where the concavity changes. So both of these will be inflection points. So let's really quick take care of that. The inflection points here are 3 pi over 4, comma, if you substitute 3 pi over 4 in here for x in sine and cosine, let's see, that is positive square root of 2 over 2, and this is negative square root of 2 over 2. Guess what? They're going to cancel each other out, and we get 0. And the same thing happens with 7 pi over 4. I just want to do one more to make sure I can make a point here. So I'm going to zoom through a lot of the work on this one. So we have this function f of x equals x plus 3 over square root of x. And here's the domain. So the domain is restricted by the square root because we cannot use negative numbers in a square root. But we also cannot include 0 because if you substitute 0 in here, then we're still dividing by 0. So we can pick anything that's greater than 0, we just cannot include it, off to infinity. So let me get the first two derivatives up here. So here we go with the first two derivatives. Now I did some simplifying to begin with. Square root became 1/2 exponent, only one term in the denominator. I can split it up into two fractions, and then I can simplify each fraction. There's 1 in the top, 1 minus 1/2 is 1/2, and I bumped this up to be negative 1/2 exponent. So I took the derivative from this function here, and then I took the derivative of this function again here, then I simplified it. So this is what I have for the second derivative. Once you set that second derivative equal to 0 and solve for x, we will find some critical values. Let me do that real quick. All right, so here we have some solving, but before I did that, since I have the second derivative ready to go, I know that the second derivative is undefined at x equals 0, which does make it a critical value. And once you start solving this, You can multiply by 4 to get rid of all of the 4's in the denominator, and then the highest power of x, so that'll completely cancel this here. And if you have an x to the 5 halves being multiplied here in the top, 5 halves minus 3 halves leaves you with x to the first. And the negative comes along for the ride. This is still positive. Solving this for x, add x to both sides, x equals 9. So here we have two critical values for the second derivative. However, since this critical value is not in the domain of the original function, this cannot give us an inflection point. We still have to use it when we are doing our number line here. So 0 is still on our number line as a critical value, but we cannot have 0 be an inflection point because it was not in the original domain. And that's really the point I wanted to make with this particular example. We could continue with 9, and then you can pick 1, and you can pick, let's say 16. And I'm picking such nice numbers because, or such strange numbers, because when you find f double prime of 1, all of these half exponents here means you will be taking a square root. So you will want numbers that are easily square rootable. And then you can go through and finish this one if you like. I will pause, you can try it, and then I'll put the answer up here for about 5 seconds and then move on to the last bit of this lesson. The last little bit here for this video, you have the second derivative test. And the second derivative test is really kind of a weird thing because it relies on the first derivative. So, I mean, you'll see, you can make your own opinions about this. The second derivative test basically says you can tell if a critical value from the first derivative is a relative max or relative min by using the second derivative. And in pictures, what that would mean is if you have a critical value that you knew of from the first derivative, like you went through, you found the critical values of the first derivative, and that critical value happened to be on a piece that was concave down, then you would have a maximum. If that critical value were on a piece of graph that was concave up, like right here, it would be a minimum. And if you had a critical value on a graph, again, remember the critical values are where the slope of the tangent line would be 0. It could also be that the critical value is neither a max nor a min. So we have these cases, but I think it makes sense. I think you guys can see if it's concave down, if the critical value lies in a concave down interval, it's a max. If it lies in a concave up interval, it's a minimum. And if it, but there's also this chance that it's not in either a concave down or a concave up. Basically, inflection points that are also critical values, those are not going to be relative max or relative min. So here's what the second derivative test says formally. So here it is. First, all of the conditions. Of course, we have to let f be a function. So f prime of c, the critical value, has to equal 0. And the second derivative exists on an open interval containing that critical value. So we have these three cases that I just sort of mentioned. If f double prime of c is greater than 0, so if the second derivative is positive at that critical value, That means it's concave up, and f will have a relative minimum at that value. If f of f double prime of c is less than 0, aka if the function is concave down at that critical value, then it has a relative maximum, as I mentioned down here. And then lastly, if f double prime of c equals 0, that's the only other option we have. We had greater than, less than, it's got to be equal. If it's equal to 0, then the second derivative test fails, and you use the first derivative test to see whether or not you have a max or a min. And I do these exercises a little bit differently, and you'll see how it's done on the next slide here. For the last couple examples, I'm going to go through them pretty quickly, but this is how I set up the second derivative test. Normally, I just give you the second derivative with some critical values, and then you just have to tell me whether the original function has a relative max, a relative min, or the test fails. So that includes two parts. You want to find f double prime of -2, which if you come up here and substitute -2 in here and here, that'll give you a +3. But most specifically, we care that it is positive. So when we have a critical value of -2, and it lies in a concave up interval, that means we can write a sentence here. Because f is concave up at the value, we'll say critical value of x equals -2, that means there is a relative minimum at x equals -2 by the second derivative test. And so this is the sentence that I am writing for this. So we can do something very similar for, let's pick the 0. F double prime of 0 equals 0 in this case, or sorry, equals, -5 in this case. And I can say something very similar, because f is concave in this case down at the critical value of x equals 0. There's a relative maximum at x equals 0 by the second derivative test. In the last scenario here, we have f double prime of 1. So f double prime of 1 in this case equals 0, and that means the second derivative test fails. The second derivative test fails at x equals 1. And because you don't have the first derivative, I don't make you go back and figure out whether it is a maximum or a minimum using the first derivative test. So this abbreviated testing of the second derivative test does a couple things for you. One, you don't have to go through and find the second derivative, because you will be doing that in other exercises when you find inflection points and intervals of concavity. Two, I can still check to see whether or not you understand how the second derivative test works. So I like these types of examples because it gets right to the point as to whether or not you understand the second derivative test. Let's take a look at one more example. I just have a couple things to say about the next example, and the lesson will be over. So here is the very last example for this video using the second derivative test. I am as excited as you are. This video took a long time to make. It will take a long time to watch. But here we go. The second derivative test for this particular function with this set of critical values is set up like this, is set up like this. I'll come back with some sentences here in a second. But the thing I want to point out here is that you may notice there is a critical value at x equals 5. Now, if you go back and look at the formal definition of the second derivative test, you will see that the critical values that we use are the critical values that make the derivative equal 0, not the critical values that make the derivative undefined. So just, if you're thinking, hey, we have this here, and this should be, 5 should be in our list of critical values, well, that's not going to help us, because that's where the first derivative was undefined. So you go through, you substitute -1 into this, you substitute 2 into this, you get some things, it's concave up, it's concave down. You can write a couple sentences that look like this, and that's it. It's because G is concave up, right? We use concave up to describe the original function. Because G is concave up at the critical value x equals -1, there's a relative minimum at x equals -1 by the second derivative test. And then a very similar statement down here. That concludes this video. Thank you for sticking through the whole thing. Remember, this is 2 lessons in 1. Good luck, everybody.